This is part 1 of section 10.11, Lagrange error bound and accuracy. So we're at the end of our study of Calc 2, and we're going to wrap this up by talking about the accuracy of Taylor polynomials. Now, we've done all kinds of approximations for functions. We've used tangent lines, we've used Euler's method, we used Taylor polynomials and Taylor series. So now what we're going to do is we're going to talk about how accurate these series and polynomials are to the actual function, if it's possible. So we're going to start by talking about error and accuracy with the remainder. So when we use a Taylor polynomial approximation, it's nice to know how accurate they are, especially if you're using them to make predictions. So it's nice to know how far off you are. So the function value by the Taylor polynomial can be defined by the concept of the remainder, which is what we did when we talked about alternating series. So it's going to be kind of similar like that. So the concept of remainder is going to be defined in this way. The function f of x is equal to the Taylor polynomial plus the remainder. So the exact value is equal to the approximate value plus the remainder. So the absolute value of the remainder, r sub n of x, is the error. So the error can be found by taking the exact value minus the approximate value. So if we look at this on a graph, and we're using a Taylor polynomial, t sub n of x, centered at x equals c to approximate the function, f of x at value x equal a near the center, we can lay it out in this way. So if the function is equal to the polynomial approximation plus the remainder, so let's write out what that looks like. So what we're saying is, so this polynomial we're trying to figure out is f of a, because we're trying to find the value of a. Remember, a needs to be near c. It can't be too far off from c. It's going to be f, the Taylor polynomial at a, plus the remainder's value at a. So what does that look like on the graph? So let's say our function looks like this. We have some nice smooth function just to make it easy. So here's our f of x, and here's c. Here's where we centered the Taylor polynomial. So here is our Taylor polynomial. Something like that. And then we're going to pick some value a, which is not going to be that far away from c. Let's say it's right here. So this is a. So the point up here that I marked is f of a. But right below it, this point is t sub n of a. So this distance right here between these two, that is our error. That's our r sub n of a. It's how far we are away from the actual function value. So if that's the case, we can find that value by taking the actual function value and subtracting the approximation at that value. So we have our error equals actual minus approximation. So that's visually what we're doing. So in order to use the Taylor polynomial effectively, we're going to use Taylor's theorem to estimate the size of the error. The remainder given in the theorem is called the Lagrange form of the remainder, or the Lagrange error bound. This gives us a bound for the error, not the exact value of the error, which is what you use more. You want to know how far off are you? What is the percentage of error? That kind of thing. So you don't usually find, oh, the error is this. You're looking for the bound of how far off you are. So here's Taylor's theorem. If a function f is differentiable through order n plus 1, so you want to take the fifth polynomial, you have to be able to take the sixth derivative in an interval containing c, then for each x in the interval, there exists a number a between x and c, such that, and there's our Taylor polynomial. Here's our Taylor polynomial right here. Oops. And then our error here at the end, as we've been saying, where the error is defined this way. Now, one thing I want to point out is that this part right here, this, I'm going to talk a little bit more, is going to be our maximum value away from C, f of C. Okay, right there. And we're going to get into that more in a second here. So instead of finding the exact error of approximations, we'll use these two rules that will help us find an upper bound for the error. And this way we will know the most that our approximation is off, so the most that it is off. So we've already done this for alternating series. So if it's an alternating series, the error will be no greater than the absolute value of the first unused term. You remember that, and that's for our alternating series. It's no greater than the absolute value. If it's not an alternating series, and it's approximated by a Taylor series, we will be using Taylor's inequality theorem, or the Lagrange form of the remainder. So here's what it is, and we just kind of stated it with Taylor's theorem there. So what we have is Taylor's inequality, which says the absolute value of r sub n of x has to be less than or equal to the absolute value of the maximum over n plus 1 factorial times the absolute value of x minus c to the n plus 1 power, where c is the center. So the maximum is defined to be the maximum value of the next derivative at that value, where x is less than a, which is less than or equal to c. So that's the Lagrange error bounds. Now this might seem like what right now, so we're going to go through and do some of these and it'll make sense. So for n equals 0, Taylor's theorem states that if f is differentiable in an interval, then there exists an a between x and c such that f of x equals f of c plus f prime of a times x minus c, or the mean value theorem. Right there, that's our mean value theorem. So we're connecting it back to what we've already done. Okay, so let's go through the vocabulary for this. So m represents the absolute value of the n plus 1 order derivative. Which we will have to find on an interval between c and x. So we're picking some value in an interval a little distance away from our center, and we're going to take the derivative at that point, and m is the absolute value of that n plus 1 order derivative. We can find m by substituting the a value between x and c that maximizes our expression. So the expression is, we're talking about the n plus 1. That doesn't look very nice. The n plus 1 derivative at a, and that's going to be the absolute value of that. The expression absolute value of x minus c to the n plus 1 over n plus 1 factorial represents the first unused term in the Taylor series. Just like we talked about that in an alternating series when we were talking about its error. We looked at its first unused term. And the product stated there. So our first unused term times the max value of the n plus 1 derivative will tell us a safe upper bound for n plus 1 derivative at x equals a. If the max of the absolute value of the n plus 1 derivative of a on the interval between the center c and the value x equal a is not given or easily found, then what you're going to do is just, because sometimes that interval is not given, so you're going to choose the first known reasonable number greater than our n plus 1 derivative at a. If you don't know the maximum or the interval, assume the interval is from the center to the x value. So you just create your own little interval. Because you know where you want to be, and you know that you are away from the center because the polynomial was made based on some center value c. So that interval is a big enough interval for you to use. And then finally, two facts about the error, the r sub n of x. First, if we increase n by adding more terms to the polynomial, the remainder will obviously, hopefully, decrease in size. Second, as we move away from the center, the size of r sub n will usually increase. Because remember, the accuracy of our Taylor polynomial or Taylor series is based on where the center is. The further you get away from the center, the less accurate it is. Okay, so let's do some examples. And I think I'll just hold the examples off to part 2.